So in this video, we're going to talk about distribution functions. So we've talked about density functions. Right? Density functions are for when you have a continuous random variable. And when you have a discrete random variable, you don't have a density function, but you do have the function of x that states the probability that x is equal to k. And when you have any random variable, so this could be discrete or continuous. By the way, you could have random variables that are somehow in between discrete and continuous. So for instance, it might take discrete values, between 1 and 10, and then continuous values past 10 or something like that. But for simplicity, we're just going to talk about random variables being either discrete or continuous. So when you have a random variable, it has what's called a distribution function. And it's the function capital F of x, which is defined to be the probability that x is equal to little x, or x is less than or equal to little x. Okay. And we're mainly going to be focusing on the case when, so mainly focus on the case when the random variable x is a continuous random variable. Right? Meaning that it takes values over the real numbers, not just integers. Well, in that case, recall that x has a density function say little f of x, then the probability that x is less than or equal to x is the integral from minus infinity to little x of f of x, right? And that's equal to capital F of x by definition. So that's the connection between the distribution function and the density function. So when the distribution function tells you the probability that f of x, the probability that capital X is less than or equal to x, and that's the area under the curve from minus infinity to infinity. So if your density function is like this, let's say this is your f of x, then your capital F of, say, x here is going to be the area. So this just goes forever. It's the area up to this point, x. So that's going to be, so this area is capital F of x. And so we see that this distribution function is increasing, right? We can think of it as like an accumulation function. So it's increasing, and then when you integrate from minus infinity to infinity, you're going to get 1. Well, when you integrate f of x, little f of x from minus infinity to infinity, you get 1. And so what happens is that the limit as x goes to infinity of capital F of x is going to be 1. Right. Or actually, we should say, when we say it's increasing, I mean it could be stable, but it doesn't decrease. Right. Okay, let's look at some examples. Well, before we get to some examples, maybe we should just observe that the probability that x is between a and b is the probability that x is less than or equal to b minus the probability that x is less than or equal to a, and that's equal to capital F of b minus capital F of a. Okay? And when x has density function little f, well, the probability that x is between little a and little b is the integral from a to b of f of x dx. Right? And so this is capital F of b minus capital F of a. And so we see that capital F is an antiderivative of little f. It's an antiderivative of little f. That's actually from the fundamental theorem of calculus, part one, or right. So this, remember, the fundamental theorem of calculus says that when you have a continuous function little f, then this function. Oh, maybe I should use a different variable here. This function is an antiderivative of little f. Right? That's what the fundamental theorem of calculus says. Okay, so that's the connection between capital F and little f. Capital F is an antiderivative of the density function, little f. So let's do some examples. So let's go back to the uniform distribution on the interval from a to b. Then, by definition, the density function is 1 over b minus a from a to b and is 0 otherwise. Right? So what's the density function? Well, it's the probability that x is less than or equal to little x, and that's the integral from minus infinity to x of f of t. And this function is, when you draw the graph, it's just this, right? That's the graph of the density function. And so the integral is equal to zero if x is less than or equal to a. If x is between a and b, then you're just integrating up to here. And so, and this height is 1 over b minus a. So it's just going to be 1 over b minus a times x minus a. And then we know that if x is greater than b, then you integrated the whole thing, right? So you just get 1. So that's the distribution function. That's your capital F of x, right? So intuitively, we think of it as, it starts up as 0, but then as it accumulates probability, it increases until you get to 1 when it's accumulated all the probability. Okay, and let's look at a different example. So this explains the concept that this probability density function is like a density, right? Because to calculate the mass, you integrate the density. Okay, so let's look at a different example. Little f of x equals rho minus 1 times x to the minus rho, where x is greater than or equal to 1, and rho is greater than 1. Well, we see that this is 0 when x is less than or equal to 1, because you're just integrating 0. And when x is greater than or equal to 1, then you're integrating, so your f of x is the integral. So when x is greater than or equal to 1, then you're integrating from 1 to x of f of t. And this is going to be rho minus 1 times t to the negative rho plus 1 over negative rho plus 1 from 1 to x. And then this divided by that's going to be negative 1. So you get negative t to the minus rho plus 1 from 1 to x. That's negative x to the negative rho plus 1 minus negative 1 to negative rho plus 1. That's just, okay, you get negative 1. So you're going to get 1 minus x to the negative rho plus 1. So it's 1 minus x to the negative rho plus 1. So that's the distribution function for this distribution. And let's also figure out the distribution function for the exponential distribution. Let's just do one more. So that's when we have a fixed lambda, and f of x, little f of x, is lambda e to the minus lambda x for x greater than or equal to 0. So again, we have the capital F is 0 when x is less than or equal to 0. When x is greater than 0, then we integrate lambda e to the minus lambda t dt from 0 to x. And this is equal to minus e to the negative lambda t, right? From 0 to x. And so this is going to be negative e to the minus lambda x minus negative 1. So you're going to get 1 minus e to the minus lambda x. And this checks out because as x goes to infinity, capital F of x approaches 1. And then one more thing is that we mentioned the standard normal distribution in the video on density functions, but that doesn't have a closed form for the distribution function. So for the normal distribution, to calculate the probability that capital X is between, say, 1 and 2 or something, then you have to use a table to figure that out. All right, so in this video, we talked about distribution functions. It's defined to be the function capital F of x, which is the probability that x is less than or equal to little x. And we've seen that when x is continuous, it's just an antiderivative of the density function, and that's how we calculate the distribution function.